this video, we're going to look at how to use the Fundamental Theorem of Calculus Part 2 to evaluate definite integrals so that we no longer have to take a limit of a Riemann sum. So the Fundamental Theorem Part 2 says the definite integral from a to b of little f of x dx is going to be capital F of b, where capital F is an antiderivative of little f, capital F of b minus capital F of a, where, as I said, capital F is any antiderivative of little f. All right, so let's see how this works. Say we want to integrate from -5 to -2 the function 1 over x dx. So little f of x is 1 over x, right? So we know all the antiderivatives of 1 over x are the natural log of the absolute value of x plus any constant. But the fundamental theorem says we just need a specific one. We don't need all of them. So let's take the most basic one. Let's use the antiderivative, capital F of x equals the natural log of the absolute value of x. We don't need the plus c at the end. So to use that, we're going to write natural log of the absolute value of -2, the upper limit of integration, minus the natural log of -5, the lower limit. And we can simplify that. That's just going to be the natural log of 2 minus the natural log of 5. And we can go a step further and call that the natural log of 2 over 5 using properties of logarithms. So first a note on notation. So we use this notation f of x with a right-hand square bracket, lower limit a, upper limit b, to mean the function f of x evaluated from a to b, which just means f of b, the upper limit, minus f of a, the lower limit. For example, 2x plus 3 evaluated from 1 to 2 is 2 times 2 plus 3 minus 2 times 1 plus 3. All right, so this is the notation we'll be using when we're evaluating definite integrals. Let's do another example. Let's do the definite integral from 1 over square root of 3 up to square root of 3 of 8 over 1 plus x squared dx. So first, we can always pull a constant out of a definite integral. So I can write it as 8 times the definite integral of 1 over square root of 3 up to square root of 3 of 1 over 1 plus x squared dx. And now I recognize 1 over 1 plus x squared as the derivative of the inverse tangent function. So the inverse tangent function is the antiderivative of 1 over 1 plus x squared. So this definite integral is going to be 8 times the inverse tangent of x evaluated from 1 over square root of 3 up to square root of 3. So now we can plug in our values. So it's 8 times the inverse tangent of the square root of 3 minus the inverse tangent of 1 over square root of 3. And now we have to remember our trig values. So this is 8 times pi over 3 minus pi over 6. And when I simplify that, I get 4 pi over 3. All right, so that's how to evaluate a definite integral without having to take a limit of a Riemann sum. You find an antiderivative and then plug in the upper limit and the lower limit and subtract. So the next thing we'll be working on is indefinite integrals, which are antiderivatives, and the net change theorem. And I'll see you there.